All right, so let's just put up in the corner here that Q as a function of T is Q max times 1 minus e to the negative T over RC. Again, worth committing to memory, perhaps. We know that Q max is going to be the EMF times the capacitance. At the same time, I as a function of T is going to be, ready, Andrew? I max.
Like movie?
Yeah, just like it. E to the minus T over RC, where I max is going to be the EMF over R. Did I really hear somebody take a picture? So let's take a look at the idea of a discharge, and I want to change the circuit a little bit to try and make a single circuit that can be used for both the charging and discharging of a capacitor. Often we look to circuits that can serve both functions. So how do I want to do this? Let me draw it this way. This is one that's been on the AP exam before. All right, so similar circuit to what we had before. The difference is that this circuit can be used for both the charging and discharging of a capacitor. It doesn't look that way because it looks like we have this EMF in there. And sometimes they'll draw the circuit a little different than this. This is, both of these have been on the AP exam. How's it look? It looks like, doesn't look like that. Don't draw that one. It looks like this, where the switch is here and can go from A to B. There, something like that. So when it's at selection A, it's a charging circuit, and when it's switched to B, it's immediately a discharging circuit. All right? So in order to actually discharge the capacitor, it has to have already been charged. I know it sounds ridiculous, but we have to now assume that at T equals 0, the charge on the capacitor is at Q max. So we are going to flip the switch from A to B, and at the instant we connect B, we have a circuit that has only 2 circuit elements in it. Now the rules for Kirchhoff's law are pretty obvious. The voltage drops will be V over R minus V over C, and that has to equal 0. Now, the question here should be from all of you, should we make this voltage positive or negative? I think it's an important discussion to have. What do you think? Yeah?
I feel like it should be positive.
And why do you feel that way?
Because the capacitor is like giving out charge. I feel like it could be something.
Now, Ricardo's observation, I think, is a valid one. When we look at the discharge of a capacitor, our voltage source is the capacitor now. Ultimately, when we look at the capacitor, we should look at it as a potential difference, and in fact that it is providing energy to the circuit. So your choice here about making it positive or negative has value. Now look, we don't, it's not like we don't know what the answer should look like. I don't think there's anybody in the room who couldn't probably cobble together what they think the answer is going to look like. At time 0, the charge has to be Q max, and over time, we know that the charge is going to drop to 0. How's it going to look? And can you kind of create the answer right now? Do it. Write down what you think. What do you think Q as a function of t will look like for the discharge of a capacitor? So Ava, what do you think it would look like?
I'm not sure.
Okay. What if I told you it's already written up there? At least the form of it is.
Is it the Q max times 1 minus T to negative T?
No, because this, we know what that'll look like. That's going to suggest the charge is going to do something like that. We know the charge on, that's a charging one. What do you think the shape of the graph would look like? Do you think you can answer that? If we're discharging the capacitor, so we're looking at the discharge of the capacitor, what do you think the graph of charge over time will look like?
Exponentially decreasing
Okay, so where do you think it would start?
at Q max.
So starting at something we call Q max, and where's it going to be over a long period of time?
It's going to go down to negative.
Yeah, so I expect it to be down here someplace, right?
Yeah.
So, do either of these already look like that?
IoT.
Yeah. If we just mimic what the current does, I think that's a pretty good approach to what we probably think the charge is going to look like. It's going to be exponential decay. And that's my expected answer. Let's see if it works out that way. Now, I think Ricardo's observation that we could probably make the capacitance positive, I don't think it's a poor observation. I think it's a good observation. I think the energy from this circuit is clearly coming from the capacitor, and it would represent a potential increase while the resistor would still be a potential decrease. Bless you. So let's go with that. Now, from here, everything we did from yesterday should be about the same. We're going to have negative IR plus Q over C equals 0. So then we're going to have negative dQ dt times R plus Q over C equals 0. And now we must go through the process of separating our derivative in order to be able to solve this differential equation. The fact that it equals 0, though, makes this one a lot easier. So I'm going to get dq dt by itself. I'm going to separate my derivative. I'm going to integrate both sides. What should I put for my limits here for Q? Yes, sir?
Should it go from Q to 0?
No, but close. I'm going to go from Q to some Q in the future. Our function should point to 0 as t goes to infinity. If I had selected this to be infinity, then yeah, I should have put 0 there. But I'm just putting this as some point in the future, so I'm just going to put the Q as some Q in the future. Does that make sense? We expect that our result will give us what we're looking for. The right side's pretty easy. It's still going to be, T over RC. We're kind of expecting to see that. But the left side, it's going to be that logarithm. So I'm going to get the logarithm of Q from Q max to some Q in the future. That's getting pretty hard to read. How about I pull up a new page? Is that okay with you guys? I made this decision, and I baited you for this. I hope you noticed that, okay? But it's because I want to be very clear in Kirchhoff's laws. unless something is actually adding energy to the system, like physically an external force on the system. Think of it from mechanics. All the energy we have was the energy that was stored in the capacitor. And it was stored because of a separation of charge. There was nothing external doing work on the charges. Because of that, we don't treat it like it's a voltage source. We treat it like we treat every capacitor ever. Every circuit element, except for an EMF, must be listed as negative unless you are in some way adding energy to the system. When you use Kirchhoff's laws, these all have to be negative. No matter what your intuition tells you about the system. The only things that you question about positive or negative are EMFs. And you have to base that on the direction of the current that you believe might be passing through the EMF. But every other circuit element's negative. And so I am in agreement with Ricardo. It feels like we should treat the capacitor as if it's adding energy to the system. But Kirchhoff's laws require that all circuit elements are treated as voltage drops. It sounds subtle, but when we make this negative, then look at what happens as a result of that decision. These both become negative. At the end of this one stays negative while that goes to the other side. So that one of them is negative and one of them is positive. That puts a negative sign right here in our integral. A negative as a result of the integral. So, logarithm of Q evaluated from Q max to some Q in the future equals T over RC. So I'm going to evaluate my logarithm, and I'll get the logarithm of Q as a function of T minus the logarithm of Q max equals T over RC. I'm just doing my algebra now. I'm going to combine my logarithm, get the logarithm of Q as a function of T over Q max. And I'm hoping you guys are seeing that this is exactly the same stuff as we did before. No surprises here? Am I okay with saying that, or is this still really hard stuff? I think this is step-by-step exactly what we've already done. I'll raise both sides to the base of E and get Q over T over Q max equals E to the T over RC. And then it should be clear we screwed up. Do you guys see how we screwed up? We made no mistakes, but we used our intuition and it failed us here. Our intuition was to state that we thought the capacitance should be listed as positive because it is adding energy to the system. That would have been my intuition and what I would have thought to do, which is why I brought it up. Years of doing this with students, sometimes the ideas we have about the way electronics should work can get us confused about what's actually happening. When that negative stays here all the way to the end. Now this is not a way of proving Kirchhoff's laws, but which one of these would make sense for the discharge of a capacitor? If we left it the way it was, that would be the charge on a capacitor over time. If we look at it now, that'd be the charge on the capacitor over time. Which one makes sense? Clearly the bottom one, right? We can't expect the charge to grow exponentially. Doesn't make any sense. So I'm bringing this up because when we deal with the discharge and charge of capacitors, Kirchhoff's laws are very clear. The voltage drop across all circuit elements except for an EMF have to be made negative. Next semester, we're going to deal with inductors. Inductors are harder in that they do what's called a back EMF. But they're a circuit element. They don't provide an actual EMF. So like every other circuit element, they're always negative. Look, this is physics. The one thing I've always loved about physics is having rules that don't vary from case to case. This is a rule. All circuit elements are always made negative in every Kirchhoff's law equation. Period. So now you've seen why. I couldn't show you why with resistors. Can show you why with capacitors. All right, that's the discharge. You should take the derivative of that to prove that the current does the same thing. So take a moment, take the derivative, and show what you get for the current. The result for the current has an important flip from yesterday. Guys done? Get I as a function of t. Do I need to wait a minute? All right, waiting just a minute. I'm going to call on one of you anyways. Probably should make it Brandon. Why? You're all caught up. Not feeling your best?
No, not.
That's okay. There's always people in the front row I can call on too.
I agree.
How you doing, Adam?
I'm good.
Did you get it yet?
No.
Okay. Are you almost done?
No.
Are you gonna be done?
Eventually.
Okay. I am patient. Maybe Kevin has the answer. Come on, guys. You're just taking the derivative with respect to t. Chris, how about you? You done?
I feel like it makes sense for me.
Sure, hope not. Guys, just chain roll, right?
Yeah.
Please be honest with me. If you guys can't do this, I will step through how to do it, but I will feel defeated. Zach?
I'm messing something up and I don't know what.
Amelia? I'm sorry, Emmanuel?
I have an answer.
Let's hear what your answer is.
Negative T over RC, E negative to the power E negative T over RC.
You have made mistakes.
Thought so.
Matt?
Isn't it just the I as a function of t equation? So I max times e to the negative t over RT?
No.
Would it be a negative version of that?
It would be a negative version of that. Yeah, there'd be a negative out front. All right, look, I didn't call on everybody in the front row, but I did call on 3/4 of the front row, and I am frustrated. Q max is a constant. So if I am taking the derivative with respect to time, and look, next time we do this, I don't want to hear, I think I'm making a mistake. Provide an answer. I'll decide whether you made a mistake or not. First things first. I'm a realist. right? I'm really talking to the people who got the answer wrong. Is that right? You just pull the constant out front. Now, when you take the derivative of any exponential, you get just the exponential back. So, but now I must take the derivative of the exponent. Well, negative 1 over RC is just a constant. So what's the derivative of t with respect to t? Front row. That's the only thing left to do here, right? I'm asking for this. Chris? It's 1. All right, so that's disappointing. I have to have a conversation with Mr. Bright and Mr. Brashear. This was not a hard one. I've seen your calculus homework. If you can't do this, you must be failing calculus. Now, it is important that we rationalize what's here. So, what I mean by rationalize, put together some meaning. Look, this is a decaying exponential. I expect to see that. I expect the current to decay. This, we showed yesterday what this is. Q over C is the EMF. Then the EMF over R is the current. This represents the max current again. There's a negative sign out in front. That shouldn't be a surprise. When the switch is over here and we are charging our capacitor, I'm going to expect the current to be traveling in this direction. You know, it doesn't travel into the capacitor. It moves charge as if the current's traveling in this clockwise pattern. When I move the switch over to here, the capacitor has been charged in such a way that now the current will have to flow backwards in order to discharge the capacitor. The charge flowed in one direction to become charged. I'm going to expect that charge having to flow in the opposite direction. So the current as a function of time actually looks, well, not quite like that. Actually looks like this. It will be negative, and it's expressly negative to indicate the current flows back the direction it came from in order to discharge the capacitor. So this negative isn't a minor thing. It's an understanding that you get a flow of current in the opposite direction. Now let's just for a moment's sake, step away from all of this so that you guys can get an appreciation of why I'm spending so much time on something ridiculous like a negative sign. If you remember from last year, we talked about waves, right? And a wave there could be some complex waveform if you want to think about music, say. Music is pressure over time. Pressure in the air. It's causing the air molecules to move back and forth. Since so many of you are interested in music at some point or another, the creation of the sound merely causes pressure changes in the air. But eventually, I'm going to want those pressure changes to be recorded someplace. Now, in the old days, that would usually mean getting those vibrations to carve something into plastic so I could play it over again. So if you look at something back in the 1800s, you get a plastic disc or a plastic cylinder. They would collect the sound using a big horn, and that horn would be connected by basically a balloon at the very end to a needle. So that as the sound came through, it caused the balloon to vibrate, and the needle would etch those vibrations into a piece of plastic so that you could reverse the process and get back the sound. The earliest recording devices were just built on wax discs. Generally, the first time you played it, you destroyed it. You got one play out of that wax disc. Some people figured out a way of casting the wax disc and creating a plastic master that they could use over and over again to make copies. Eventually, this became the phonograph. The recording of it electronically took a lot of years of development. And the way that we moved to shortly after this was magnetic tape. Magnetic tape used an electromagnetic field to record the music, which meant at some point or another, a current had to be produced in both a positive and a negative direction to cause the field to be going backwards and forwards. Now, the intricacies of this I won't get into, but I need you to understand that what we are doing right now is building the basics of a filtering system that would help us filter out some sounds versus other sounds. So paying attention to the direction of current stored in a capacitor or used by a capacitor has exceptional value. And understanding the difference between the current being positive and the current being negative will have more far-reaching consequences. I don't want you to ever think of a negative sign as just a negative sign. I've talked about it twice today, the importance of being careful about the way we phrase something. By the way, this resistor capacitor is called a low-pass filter. And anybody who knows anything about stereo equipment knows that a low-pass filter is a crossover. It's why your speakers have more than one driver, to send the low notes to one driver and the high notes to another. Does that occur to any of you? Do you guys know what I'm talking about at all? This is all it is. We'll be able to show later that you can filter sound by using this exact same setup. It's not just about timing. The timing here can be used to determine the frequency that's filtered out. So I do want to pay attention. I want to be aware of the differences and the intricacies between positive and negative. All right.